All right, we're moving on to optimization, and I'm very, very sad to tell you that as much as you've enjoyed related rates the last couple of days, we are sadly moving on, and we're going to leave them in our rearview mirror for a little while. But don't worry, they'll show back up on your tests and your spirals, so they're not too far away. But today we're going to talk about optimization, and certainly another challenging topic to say the least. But let's get right to it. Optimization is the ability to find the single value that either maximizes or minimizes a particular function. The one thing that that does intrigue me about this topic is it seems to be very applicable to the real world, and we'll see some examples today that'll kind of get your brain working a little bit, and you can start to see where, as an engineer out in the real world, how this concept of maximizing or minimizing a function could be very practical. Such as, we might be maximizing some volumes, we might be minimizing the distance traveled, we might be minimizing the area of a certain geometric shape, we might be minimizing the length. All sorts of things that fall into this neighborhood are what we're going to tackle today. All right, I want to do a brief overview of the steps we're going to take on these problems, and then as we do go through the problems, I'll kind of point out how each of these steps was incorporated and how it's going to reveal itself. But first thing we want to do is we want to write what I call a primary equation. And that primary equation basically is for the quantity that's either going to be maximized or minimized along the way. And then and this is maybe my favorite step, the most important one, we want to try to reduce that primary equation so it's in terms of only one variable. And once in a while we'll get lucky and we'll start off with just one and we don't have to worry about this step. But I would say 90% of the time it's going to be in terms of multiple variables. And in order to combat that, we're going to write what I call a secondary equation with a fixed amount, and then we're going to substitute that into the primary so that we could, like we said, reduce it to just one variable. And again, if that sentence right there seems a little confusing, don't sweat it. When we jump into those first couple of examples, I think it'll make a lot of sense. The third step, I want you to always just determine the domain. I think this will really be a practical practice for us, and it just basically consider what's realistic in the real world. Like, is it really feasible for some of these problems for x to be, a negative number? Is it possible for it to, there's a lot of cases x can't reasonably go beyond, some kind of upper limit. So we want to think about the domain, and then we just want to find the desired max or min value, depending on the problem, using good calculus techniques. All right, let's jump in. All right, so here's our first example, and they want us to find two positive numbers where the sum of the first and twice the second is 100, and the product is a maximum. So let's start off, and I just want to get used to this terminology of a primary and a secondary equation. And again, the primary equation, I defined it as the equation that needs to be either maximized or minimized. So in this case, we're trying to maximize the product of two numbers, and let's just say x represents the first and y represents the second number by definition. So we'll say that the product equals x times y, and that's the one we're trying to maximize. However, you'll notice that the product is being expressed in terms of two variables, x and y, and that's a no-no. So I want to try to somehow come up of a secondary equation, and I said you want to use the fixed amount. In this case, what's fixed? They said that the sum of the first two, for the first one and twice the second, has to be 100. So let's say 100 equals the sum of the first and twice the second. So because the 100 was the fixed amount, this is what I call my secondary equation. And what we're going to do is we're just going to isolate whichever variable seems to be easier to isolate. And in this case, I think the x is easier to isolate because it doesn't have a coefficient. And now I'm going to take this expression right there and I'm going to substitute into that x. And we're going to rewrite the product as 100 minus 2y times y. We'll clean that up just a touch, and that's going to be 100y minus 2y squared. All right, so we've got this formula for product. And now they want me to either maximize, or in this case, maximize this function using good calculus techniques. The domain is not of particular interest to me on this one. It's wait till we get into a more practical, real-world scenario before we talk about that. But here's the magical part, and this is what the class is all about. The ability to, no matter what the function does, okay, when it hits its peak, when it reaches its maximum point, the one thing that has to be true is the fact that the slope at that one moment is 0. All right. And so we're going to take advantage of that concept and say, well, here's my derivative, 100 minus 4y. Notice the derivative was with respect to the independent variable, which was in this case a y. That's unusual. Typically y is the dependent, but in this case p was the dependent, y was the independent variable. So just make a note in your notebook that the derivative is with respect to the independent variable at all times. It's not with respect to t necessarily, like related rates. Now what I'm going to do with that derivative is I'm going to set it equal to 0. I'm going to say that 100 minus 4y has got to be 0 because the slope was 0. It's guaranteed. Therefore, 100 equals 4y. 25 equals y. Now the only trick about this right now is we've only proven that the slope is 0. I haven't really proven that it's a max versus a min. So I'm going to construct a really quick, snappy sign chart. And if I plug something like, if I plug a 1 into the derivative, I got a positive, which is good. And if I plug something like a 50 into there, I got a negative, which means the p function's increasing, then decreasing. And I've just proven that if we let y equal 25, this will maximize the product. The only thing missing is I should probably find x. So let's see, what did we say? We said earlier that 100 is equal to x plus 2y. So we just proved that x also is 50. So y is 25, x is 50, and that'll satisfy the question. This is one of my favorite problems of all time here. It says a farmer plans to fence in a rectangular pasture that's adjacent to the river. So we've got our beautiful river right here. And what we're going to do is we're going to fence a pasture in, just like so. And the pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing in order to reduce the farmer's expenses? We want to be very financially responsible here to be a good business person. So let's talk primary and secondary. Primary, what are we trying to minimize here? We're trying to minimize the perimeter. And let's see, so I think in the perimeter, if I said this is x and this is y, the perimeter in this case is going to be 2x plus 1y. I don't need any fencing along the water. That's the one thing to take into account here. Now the secondary equation would be the one that's fixed, and I would say that the area is fixed. It's got to be 180,000 square meters. Again, just look at your units. That kind of tells you that it's area, in case you were wondering. And so what I'm going to do is I'm going to isolate, let's say I'm going to isolate the x. So I'll just divide the y over, and I've got my x. We'll substitute that expression in for this x. Certainly didn't have to isolate the x. We could have isolated the y, and perhaps you could make a stronger argument that that would have been a better idea. But let's see here. P equals 2 times that expression. So I'm thinking, is that going to be 360,000 now? Divided by y plus y. So now we've expressed the perimeter in terms of one variable only. We're going to try to derive this sucker. Again, I'm visualizing in my mind that the first term is really y to the negative 1. So then the derivative is again with respect to y coincidentally. And it's going to be negative 360,000 y to the negative 2 plus 1. We're going to set that bar equal to 0. That's the one thing that's guaranteed to be true at whether, just imagine a minimum point on any function. The slope's guaranteed to be 0. So let's say that I'm going to add that first term over. 1 equals 360,000 divided by y squared. Cross multiply. Got our y squared over here. We'll take the square root, and that looks like to me, so I got 600 for the square root. And again, the trick is we don't know whether that's a max or a min until we prove it with a sign chart. And I know, certainly what we're expecting to be true. We just need to go prove it and verify it. Oh my goodness, I forgot to talk about the domain, and I actually wanted to talk about it this time. A reasonable lower limit would be 0. And the only reason I throw that out there is because I just want you to use your common sense when you're solving problems like this. And if we, for some reason we got a negative answer right here, I want your common sense to kick in and really just, have a strong conviction that that's got to be a wrong answer and be able to go back and trace through your mistake. But anyway, for the derivative, when we plug back in, I want you to picture 1 minus 360,000 divided by y squared. And so if I substitute a 1 into that expression, I definitely get negatives for p prime. And then if I substitute something like 700 into there, I'm going to get positives. And therefore p is decreasing and then increasing. So if we let y equal 600, that'll minimize the amount of perimeter or fencing we need. And of course, we could substitute the 600 back into the secondary equation, and I believe it said 180,000 equaled x times y, and then just divide the 600 over, and you would have your x value as well. Here's another really popular AP style question. They want you to consider the region enclosed by the x-axis and the curve f of x equals 9 minus x squared. So let's go ahead and come up with a really nice drawing here. And we've got a parabola that intercepts the y-axis at 9, and we've got roots of negative 3 on that side and positive 3 on this side. Alright. Okay, and here's what they want us to do. They want us to find the dimensions of the largest rectangle possible that can be inscribed within this region, assuming that its base lies on the x-axis. So what I'm doing is I'm kind of picturing some kind of a happy medium rectangle that looks like this. And of course, you could kind of, you could make it taller, but if you made it taller, then it would be more narrow. Or you could go the other way. You could make it shorter and a little wider. And we're just trying to experiment and work, or kind of fidget around until we find the biggest possible rectangle. And of course, I think you'd all agree that there's an infinite number of designs that you could create. And out of that, all those possibilities, we want to find the single biggest rectangle possible. So what I'm thinking here is, let's just pick an arbitrary vertex there that falls on the curve, and that ordered pair right there is x comma y. And basically what that says is, if we start at the origin, we would walk to the right x units, and then we would walk straight up y units. And so by that little picture there, we could say to ourselves that the area is really 2x for the entire base times the height of y. And this is my primary equation. The only problem is it's in terms of two variables. The secondary equation here is a little more subtle. The original function they gave us is the secondary equation. They're really telling us that y equals 9 minus x squared, and so we're going to go ahead and substitute that secondary equation into our primary. If you took the derivative right now, you'd have to use product rule, so I want to try to stay away from that, and I want to distribute the 2x. I think that makes good sense here. And so now a is a function of x, and I want to take the derivative with respect to x. And we've got this bear. Now, I'm rushing myself here, and I forgot to talk about domain again. I'm kicking myself in the butt. What's a reasonable domain for x as we solve here? Certainly expecting x to be positive, but you'll notice the picture convinces me that x can't possibly be bigger than 3. So I'm thinking a domain somewhere between 0 and 3, non-inclusive, would be my expectant domain. Again, the reason that's valuable is because if you do all this crazy number crunching and you get to the end and you cross the finish line and your answer is like x equals 4, then by golly, something ought to kick in and cause you to second guess and question that answer. Anyway, back to this derivative. Of course, we're now going to set this derivative equal to 0 because the function's got to have a slope of 0. And let's see, 6x squared is equal to 18, x squared is equal to 3, and so I'm going to say, and I'm not going to worry about the negative, I'm just going to say positive radical 3 because of the domain. I'm going to instantly reject negative radical 3, and I'm going to construct, the square root of 3 is, approximately 1 point something, 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 so that seems like a reasonable number that, x could possibly be. We'll throw radical 3 here. I'm going to use my domain as endpoints, and I'm going to substitute a 1 back into the derivative, and I got positives. So, of course, the area is increasing throughout that interval. As x grows from 0 to radical 3, then the areas are going to increase. If I substituted a 2, let's see, that would certainly give me a negative answer. Therefore, the area is decreasing, and we've proved that if x equals radical 3, we maximize the rectangle. Now, just be careful. The question actually asks for the dimensions. In the dimensions, I would say the base is going to be 2 times radical 3. And I would say that the height has to be, well, let's see. We knew that the y was equal to square root, nope, I'm sorry, I'm thinking of a different problem. 9 minus x squared. And if I substitute the radical 3 in there, I'd end up with 6 for the height. All right, our last problem for tonight is, as you would expect, our most intense problem. And not only is the calculus going to be pretty intense, but like most of the problems we've seen lately, just the basic, arithmetic and algebra can be pretty intense. But what we've got here is we've got our level ground here, and we've got two posts. One of the posts is 12 feet tall, and the other post is significantly taller at 28 feet. Try to squeeze that in there. Okay. And they stand 30 feet apart. So the total distance from here all the way over here is 30 feet grand total. Now what's going to happen, they're to be secured by two wires attached to a single stake running from ground level to the top of each post. So basically what's going to happen is we need to put somewhere between those, we need to pick a point where to put our stake. And then the wires are going to be attached to that, from that stake to the top of each post. And what I'm trying to do is I'm trying to figure out where exactly should I put that stake in an effort to minimize the amount of wire used. And, should I put it closer to the 12-foot post, or should I slide it over to the left? Should I shimmy it this way a little bit and get it closer to the 28-foot post? Or should I just put it smack dab in the middle at 15 feet apart from each post? That's the million-dollar question. So what I'm going to do is I'm going to try to come up with a primary equation that represents the total length of the two wires. And, I could say, if we said that the distance from the stake to the first shorter post was x, then that would mean that this other gap over here is 30 minus x. We got that much left over. For the two wires, we could say, well, let's say this guy's y and this guy's z, perhaps. Or you could pick your favorite variables. And I'm just going to use the Pythagorean theorem to figure out the length of each of these rascals. So let's see, on this first one here, I could say that 28 squared plus the quantity 30 minus x squared equals y squared, and y is equal to the square root of all of that. And we may decide to FOIL this one out, but I'm going to hold off until I can make a better decision as we get into the problem. On the other side, we're just going to say, x squared plus 12 squared equals z squared. Therefore, z itself is the square root of x squared plus 144. Now, we're trying to minimize the length of the wire, so I'm going to say that the length of the wire is the sum of those two ugly radicals. So we've got ourselves, I think 28 squared is 784. You can holler at me in class tomorrow if I'm off on that. And let's see, whoops, I want to scribble that out. Then we'll just do the sum, and we'll get the second radical in there. So that's the length of the wire right there. And the good news is, and this will sometimes happen, we're already in terms of one variable. So we're not going to make a big deal out of, who the secondary equation is and such. L's already in terms of one variable. What would be a good domain for this particular problem? What is x allowed to be? Certainly, I think you'd agree that x has to be a positive number, and I think you'd certainly agree that x cannot exceed 30. That would cause some serious problems. So again, if we get an answer smaller than 0 or bigger than 30, certainly the red flag should go up. Now all I'm going to do is I'm going to try to take the derivative of L with respect to x. We're going to fight through some interesting chain rule, and we'll see if we can't set that derivative equal to 0 and solve it. So what I'm going to encourage you to do here is I'm going to encourage you to hit the pause button, run through your chain rule, and you might have a couple layers of chain rule if you didn't FOIL out the 30 minus x like I didn't. Anyway, let's come back in a few seconds and compare our derivatives. Okay, so I hope that our derivatives look somewhat similar. This is the chain rule here on the first uglier radical. I started deriving the inner function right here. Don't forget that the derivative of the inside right there did give us a -1. Don't lose that -1. Something as innocent as that little rascal could really derail the entire problem. And then I've got my plus sign, and I finished the derivative of the smaller radical. Much friendlier chain rule right there. What I'm going to do is I'm just going to kill a few things here. I've got a 1/2 times a 2. Those always cancel out. And again, a 1/2 times a 2, so that was nice. And I'm going to rewrite these so it's a little friendlier looking. I've got, I'm going to multiply the -1 through there. So I've got positive x minus 30 all over the square root of 784 plus the quantity 30 minus x squared. Again, negative exponent, put that radical on the bottom. Plus, let's see, what do we got here? x over x squared plus 144. And let's see, slab square root. Number one thing I want us to walk into class tomorrow and be able to do is to recognize that once we take the derivative, we're going to set it equal to 0 every single time. And then all I'm going to do is I'm going to just move one of the terms over. Once I move that term over, I'm going to cross multiply, and then I'm going to square both sides to kill the radicals, and we're off and running, okay? But that's beyond really what I want to cover tonight. I want us to be able to write our primary equations in terms of one variable. I want us to clean them up the best we can before we rush into the derivative. I want us to differentiate with respect to the independent variable, and last but not least, I want us to be able to set that derivative equal to 0, and then finally critical points and prove whether it's a max or min with a sign chart. So I think we're ready to rock and roll. We got one more big class day tomorrow before we hit our test. So things are really building up in a hurry, and we're excited and ready to rock and roll. So good job tonight. Way to hang in there, and I will see you tomorrow.